Okay, this is a video recording of Lecture 7 for Sustainability Modeling Spring 2013. I'm going to fire up the screen show here. And let's see. Here we go. So this lecture is on HANDY, and this is a system dynamics model of human and nature dynamics. And again, this is Sustainability Modeling Lecture number 7. I want to make a few acknowledgments. First, this lecture is based on the work of my colleague Safa Motshare and collaborators, Jorge Rivas and Eugenia Calnay. And you've seen the HANDY paper, which we've distributed, which is in review for publication, and also earlier contributions to the same work. And I want to ask you to see the readings that have been placed on our class Dropbox folder under HANDY. There were a couple of links here that I added for some additional documentation you can take a look at. There's a poster was presented at the fall meeting of the American Geophysical Union last year, and there's another document that you can take a look at. And this is basically a synthesis of this work done by these colleagues. Let's talk a little bit about the HANDY model. First, as we said, it's a human nature dynamics model where population is divided into two cohorts. And the two cohorts are elites and commoners, and we'll explain a little bit more the differences between these two. Nature is also a stock that has regeneration and consumption by population, and we'll look into this mechanism. And then there's an additional stock that we call wealth, which is created as a result of consumption of nature. Okay, and this wealth, once it's created, is also consumed by population. So you have essentially, this model has four stocks. It's got two cohorts of population, nature as a stock, and then wealth. Okay, and then there's interactions, and we'll see a little bit of the diagram of that. Before we go into that, I want to show you the governing equations. Again, we have four governing equations for the four stocks. The variable x sub c is the population of commoners, and the variable x sub e is the population of the elites. Nature is denoted with y, and wealth with w. Now let's take a look at the right-hand side of each of these equations. The left-hand side denotes the rate of change of each of these, and the right-hand side are the drivers of these change, positives and negatives, indicating fluxes in and fluxes out of the system. So first, the commoner population. If you look at the dynamics, it's got a growth of population that is proportional to the population, and this would be this coefficient beta would be essentially a growth rate, and then it's got a death of commoner population, which is driven by a decay rate or a death rate of commoners. Okay, so it's fairly straightforward, very similar to the nature population model that we saw last lecture. The elite population's got similar dynamics, only that with with other parameters. It's got a growth driven by a coefficient beta and a death driven by a coefficient alpha. Okay. Nature's got a also positive and negative sides to it. The positive side of nature is what we call the ability of nature to regenerate, and is driven by something very similar to a logistics equation. You have a regeneration rate gamma times the nature stock, and then also driven by the difference between the nature stock and some maximum nature capital or carrying capacity for nature. And this is essentially this lambda parameter is used to denote the value of nature in the absence of essentially of depletion. So that's the value of lambda. And then it's got consumption of nature. Consumption is driven by, you can see here, the commoners are are the ones that consume nature. So the elites don't consume nature directly. Okay, and that's an important factor in this model. And that consumption is driven by a consumption rate delta. Okay. And lastly, wealth. Wealth is produced by the consumption of nature. So these two terms are equivalent. And then wealth is consumed by the commoners here and by the elites. And what I will do next is take a look at each of these terms, individually. So we can summarize a few observations. First, that the birth and the death rates can be different for commoners and elites, and in particular the mortality rate, the alphas, in this case are linked to wealth, and that's an important link between mortality and wealth in the system. Nature is bounded by so-called natural capital, lambda, which is the size of nature in the absence of depletion. I mentioned this before. And only commoners deplete nature. And this is typical for the example to denote extraction of resources, so that elites are modeled to represent more like executive management and supervisory roles within the population, not directly involved in the depletion of nature. Okay? So let me walk you through the relationship between the mortality rate alpha and the wealth. Okay, and essentially what's referred to here is that first of all, let's look at high values of wealth. If there's a lot of wealth in the system, and this wealth is expressed as a ratio between the wealth in the system and some threshold that we'll define in a second, it's used to denote the minimum wealth that is required to sustain population. So if you are at values of wealth that are much greater than that minimum threshold wealth, then your death rates fall to a minimum. And that means there's enough wealth to go around, so people may have money to spend and stay healthy, and so it minimizes and this would fall to a minimum death rate, maybe some natural death rate. Now, if you start, running into lower values of wealth, then you will reach a threshold, and the threshold is going to be different for the commoners than for the elites. So actually, the elites are able to subsist at a much lower level of wealth. That's denoted with this coefficient kappa, which is an inequality ratio. And we'll see more of this in a second. But essentially, once you hit these thresholds for the commoners and for the elites, then the death rates start increasing very, very quickly, and then you have a maximum death rate up here. That is common to both populations, although it doesn't have to be. You can actually conceive these to be different. But so this is a nice picture to represent a relationship between death rate and wealth in the system, and also inequality between the two cohorts of population. Let's talk about the consumption rates that appear in the equations. And so the consumption by commoners that appears here first. This is the consumption by commoners. It's expressed as the population of commoners. So the total consumption by commoners is a factor. It's proportion, or it's proportional to the population of commoners, times S, which is used to express a salary per capita. Okay, so now we're translating this into monetary value. And then the minimum between 1 and this ratio, again, of wealth by some threshold wealth. Okay, and this is meant to imply that if there's plenty of wealth by which this ratio will be larger than 1, then consumption is basically salary times population. However, if if you start running values at value of total wealth in the system that are lower than that threshold, then you're going to have to, essentially, the system reduces consumption. If there's scarcity of wealth, then both commoners and elites, both will follow the same pattern, will be able to consume less. Okay? The difference between the consumption of commoners and the consumption of elites is that the elites consume more, driven by this inequality factor kappa. So this is a factor that's non-dimensional and that has essentially it's larger than 1. So the elites consume more per capita than the commoners. Now this value, this threshold value of wealth, it's essentially the minimum wealth that is required to sustain a population, a combination of population of commoners and elites, each consuming at their per capita value. Okay, and that's why the elites are multiplied by kappa. Okay. And that conversion between population to wealth numbers, it's this factor of rho. Okay, so rho could be seen essentially as a wealth per capita, minimum wealth per capita produced. Okay, so let's take a look at how this consumption or these consumption rates look, and what you'll see here is something very, very similar. Again, we have these plotted as a function of this ratio of wealth to minimum wealth, and then what you have is that the commoners, if you have plenty of wealth, will consume simply at the ratio, this ratio, which is 1. So the consumption will be simply equal to salary times the number of people in the commoners cohort. If the same applies for the elites, only that they'll consume at a rate of kappa times higher than the commoners. Okay. Of course, if you start running low on wealth, then you're going to see that these two curves start tapering down. That means that consumption is adjusted in times of dire wealth. Okay, and the adjustment is essentially this ramping down of these two relationships. Okay, so that's essentially very, very, very simple formulation. So we can make a few more observations. So this model considers a minimum wealth which is required for subsistence. Below this threshold, there's essentially famine. Okay, and this threshold is calculating using a minimum required consumption per capita, which is rho for the commoners and it's kappa rho for the elites. So that's the minimum required consumption. And this salary differential factor or inequality factor kappa, it's an exogenous variable, so it's assigned externally, but in reality, it would be calculated endogenously through other variables in the model. So that's actually one thing that's being improved on this current version of Handy. So we're going to be doing an additional video to walk you specifically through the Venson model, but I wanted to sort of walk you through the general structure, and then what you have is the 4 stocks. Okay, the elite population, the commoner, nature, and accumulated wealth. The elite population has a birth rate and a death rate. Okay, the death rate is driven by the threshold, so the maximum alpha capital M and the minimum alpha little m, the inequality factor, and we'll see what these shadow or grayed out variables mean, and the minimum wealth, and those actually drive not only the death rate of the elites but also the death rate of the commoners. And the commoners have essentially the same structure, births and deaths. And the deaths are driven by the wealth. Okay, you can see the connection between wealth and minimum wealth into these death rates. Now let me take a look at this side of the model. You have nature. Nature has the ability to regenerate. and the regeneration of nature is driven by a regeneration coefficient, and the lambda, this natural capital or the natural carrying capacity for the nature stock. And nature is depleted or consumed by production. Production is driven by the production factor and the population of commoners. Commoners extract nature to produce, and production then feeds wealth. Okay? Wealth is consumed by both cohorts of population, and the consumption rates here and here are driven by the value of wealth and its ratio compared to this minimum, and the salary. And in the case of the elites, the inequality factor, or this salary differential factor. And that's how the dynamics work. Essentially, populations grow and die. The death is tied to wealth. Okay, wealth is produced through consumption of nature, and in the consumption of nature, the commoners intervene, and nature is able to regenerate itself. So it's basically nature is renewable to some degree. Okay, so that's the general structure, and we'll go into more specific detail by looking at the Venson model for this. What I have here is one of these scenarios that it's run, and this is just taken straight out of the Venson simulation, and I won't dwell too much in that, but I did want to show the 4 stocks that are being plotted over time, and this is a simulation of something like 500 years. In this particular scenario, what you can see very quickly is that the commoners in blue are able to grow by depleting nature. Okay, and in doing so, they enable also the growth of the elite, which are in red. Now, both populations, essentially draw nature down. The commoners directly through extraction, the elites by interacting with the commoners, and through wealth. So, in growing and in depleting nature, wealth is produced. At some point in the process, because of this combination of parameters, what's going to happen is that you run out of natural resources, which disables essentially disables the production of wealth. So wealth comes down, and then this eventually causes the collapse, the crash of both populations at the end. Okay. Interestingly enough, the elites take longer to develop, but they're the last ones to go. So one of the things that is important to consider in this work is the concept of sustainability and equilibrium, and essentially these two concepts at some level they tend to be equivalent, and the idea is that in order for population, both common and elites, to reach equilibrium, to reach a value that is not zero, so it's not collapsed, that is sustainable over time, there are a number of conditions that need to be met. And let's try to go through these more or less intuitively. First of all, the birth rates of the elites and the commoners need to be greater than the minimum death rate. Okay, otherwise, neither population can attain growth. Okay, so there has to be, this condition has to be met. Okay, that's first condition. The second condition is that both of these growth rates, so the birth rate of elites and the birth rate of commoners, need to be less or equal than the maximum death rate. Okay, and the reason for this is that if this doesn't happen, then the population growth could explode or would explode, because if the birth rate exceeds, if these birth rates exceed the maximum possible death rate, then there's no way then death can catch up with births, and then population would explode. So these two actually are complementary. These keep population in check at some sustainable level. Then another condition is that the birth rate of the elites needs to be less or equal than the birth rate of commoners. Otherwise, the elites would overrun the commoners, and because the commoners are the ones that are producing the wealth, then the system would collapse. So this condition needs to be met. Okay. So you've summarized these. If you put all all these three conditions together, you get this nice relationship that needs to be attained for sustainability to be met. Okay, if any of these conditions is not met, then you won't reach a sustainable system. Now, it's important to say that these are minimum conditions for sustainability. So it's really they do not guarantee sustainability, but they are required for sustainability. Okay, so if these are not met, you won't get sustainability. If they are met, you may achieve sustainability. In short words. So let's look at the scenarios that are described in the handy paper. The first scenario is referred to as the egalitarian society. Egalitarian society meaning there's no elites. Basically that x sub e is 0, identically equal to 0. There's no elites. In the second scenario they consider is the equitable society. In this case you have commoners and elites, but they have equal salary for both. So this kappa coefficient is equal to 1. And the third scenario, which is perhaps the more general, is you have commoners and elites and there are unequal salaries. So there's a kappa that's greater than 1. There's some common model parameters that are described in the paper, and those are it. And these are the ones that are in the Benson model as defaults. So you have here the minimum depth, and these have units, and in the model itself, we do include the units just to be consistent. I would have preferred that if in the paper they had included the units. I spent a lot of time kind of putting the units in place in the Benson model. But anyway, so here we are: alpha little m, alpha big M, beta c, beta m. Beta c, beta e for the birth rates. You have the nature regeneration rate and the natural capital. Okay, you have the salary, and you have the minimum wealth that's required per capita. You have the initial population of commoners is 100. The initial nature equal to natural capital, and the initial wealth is 0. So these are all common parameters used in these scenarios, and then the different scenarios have different sets of other parameters that you need to introduce. So let's take a look at the first scenario, the egalitarian society in equilibrium. Okay. So the sustainable equilibrium solution, and I'll ask you to look at the notes. I did a little bit of algebra there to derive these values, but essentially these are the equations. And in the egalitarian society, you have no elites. So you get three sustainable stocks in equilibrium. You have the commoner population in equilibrium, the nature in equilibrium, and the wealth in equilibrium. Okay, and these are essentially the relationships, and you can calculate these given the parameters. So this value of population in equilibrium can be interpreted as the carrying capacity for population. And this is the population value that is sustainable by the system. Okay, these two are essentially the associated values of nature and wealth that are sustainable by the system. So this set of population, nature, and wealth are sustainable under these conditions. Okay, so you can reach sustainability and avoid collapse in this case. Now, something that in the paper it's explained thoroughly enough that I wanted to bring up is the relationship between the carrying capacity and of population in this case and the rate of production. Okay, now the rate of production is essentially the rate at which nature is consumed. Okay, and you can actually you can find the value of the production rate, delta, that maximizes the carrying capacity of population. So you can find through analysis, and it's a very simple analysis, and there's I did some notes for the derivation of that that I've included with this lecture. It's you can find the production rate, the rate at which you're consuming nature, that will help you maximize the population that's sustainable by the system. So that's an interesting concept. And in this case, if you do the math, you find that production rate that maximizes the carrying capacity, it's equal to twice this eta parameter that's in the notes times the salary divided by the natural capital. So using the parameters that we just discussed, this value yields a delta star of this number. And you can actually use this value to explore the dynamics of the system if you deviate from the sustainable equilibrium. So if you start, for example, depleting nature at a faster rate than this, and look at the units. The depletion rate has units of per people per year. So this is nature depleted per unit person per year. Okay. So you can see, well, what happens if you deplete nature at a faster rate than this or a lower rate than this? What happens to the population? Is it sustainable? Is it not sustainable? Does it, what value does it achieve? So it's interesting to see those dynamics. So these are a few of the results, and I wanted to go through these, and so we can look at the first scenario. So this is a scenario in which it's scenario one. So there's no elites. So there's only commoners, wealth, and nature. And you can see that in this simulation, you do get an equilibrium. After some time, nature is depleted, but eventually stabilizes. Wealth is created, but eventually stabilizes, and commoners grow, but eventually they stabilize. Okay, and this happens at that value of production rate that we just saw. Okay, so that's one result, and these are the values at which it stabilizes. Remember that this population started with 100 commoners, so it ends up being more like 80,000 commoners, and you started with I believe. A value of 100 in nature, and this nature is measured in eco-dollars, so you start 100 and you end up at something like 50. In terms of wealth, you start at zero wealth and you generated 400 eco-dollars of wealth. So that's interesting in itself. So that's one scenario. This is a second scenario, and this happens when you start consuming at a delta that is 2.5 times the sustainable delta, or the delta that maximizes. And when you do that, then when you can start seeing is that you actually get some this phenomena of overshoot, where you exceed your carrying capacity, and then the system self-regulates. So remember that nature gets regenerated, so it may go down, but then it gets regenerated, it goes back up, and then it comes down again, and eventually it stabilizes at a much lower value, by the way, and so does wealth, and it does the same thing, and the commoners. So all the variables oscillate, they go up and down, and they oscillate until they're able to find their sustainable values. Okay, so that's another interesting result by consuming at a faster rate. If you push it even further, so now you go to a value of 4 times that for the depletion rate, or for the production rate, then you start seeing these cycles of depletion and prosperity, and depletion and prosperity. I think it's discussed here. Okay, and again, because of nature's capacity to become regenerated. Another scenario, this is a collapsing scenario in which you're pushing the system too hard, and there's, in this case, nature doesn't get a chance to regenerate. So once nature crashes, it's done, and then the wealth, which grew for a while at the expense of nature, will crash, and the commoners, which were able to grow because there was wealth at the expense of nature, also crash. So that's the again, and it's so you can actually start looking at how the different stocks interact with this single parameter, which is the production rate. So let's take a look at scenario 2, which is the equitable society in equilibrium. And again, you can do the same, very similar analysis and find sustainable equilibrium solutions for in this case the 4 stocks, because now you have the essentially the commoner population in equilibrium, the elite population in equilibrium, and even though there are commoners and elites, and they're paid the same because the equitable society has an equal pay for both. You do get the segregation between the 2 stocks, and then you get the nature and the wealth in equilibrium. So these two together. If you add these 2, then you get the carrying capacity for population, and this is the population value total, commoners and elites, that is sustainable by the system. Okay, and then in turn these other 2 will give you the associated values of nature and wealth that are sustainable by this system. This parameter phi that appears here, which is new, is a ratio of the initial elites to the initial commoners. So this is the initial proportion of elites to commoners, and the production rate that results in order to maximize the carrying capacity for population, it's here. Okay, and for example, if you set 0.25 as this ratio, so if you have initially a population of say 100 commoners and 25 elites, so this proportion is 0.25. This yields you a value of delta, and I'm calling this delta star star to follow the notation in the paper of this value. Okay, and then you can look at, like in the paper they do, at results varying the delta, the production rate with respect to this value. Okay, so this is the first scenario, and this scenario is what was referred in the paper as soft landing, and basically this is it means that you achieve a sustainable value for the commoners, for the workers, for the non-workers, which are the elites, for nature and for wealth. Okay, and in this case, delta is equal to that optimum value that we found. Okay, so this is the sustainable scenario in which the sustainable populations are arrived in a smooth way. So that's the soft landing characterization. Again, if you push the production rate higher, then you start getting these oscillations. So this is no longer soft landing; it's very bumpy landing. But again, if you look at the longer time, the system is able to stabilize elites here, commoners here, wealth here, and nature here. So you do get, you do get stabilization. You do get stabilization at lower values. So it's less than optimum, but it is sustainable. If you push it even harder, if you push the production rate even higher, then you start getting the higher oscillations, the cycles, the cycles of prosperity, overshoot, and collapse. And essentially, you can see the nature, goes down, collapses completely, and for a while there's no nature, so everybody else collapses, but nature then is able to regenerate. Okay, and remember that the nature regenerates because the regeneration term in nature is proportional to it, because it has this natural capital built in. So it's able to bounce back. Once it bounces back, then it enables again growth of populations, both populations and wealth, and then it crashes again because of consumption. And you see these these cycles. Okay, one can wonder. I mean, if something like this is what happens to the Mayas, but they were never able to come back, and which might be more an example like this, which is full collapse. And at this point, there's no ability of nature to regenerate. Consumption here is much too fast. The production, which is essentially depletion of nature, is too hard for the system to recover, and then you get full collapse. And here is an interesting scenario. It's a scenario in which the initially they essentially raised the proportion. So this flips the system around. This says initially there are more elites than commoners in the system. So there's 6 times here, 6 times more elites than commoners. Okay. So instead of 25 elites to begin with, you start with 600 elites and 100 commoners. And what this does is that it's able to lower the depletion per capita because you have more people in the system to begin with. Okay, and that's essentially what you do is that you're able to, at the same production rate, you're able to you produce the same. There's more people, so there is less less consumption per capita, and this is able to stabilize the system. So that was an interesting result that they explored in the paper. Okay, that's probably not obvious. Then you can look at the sort of the full Monty case. You have the unequal society in equilibrium. So here now you have commoners and elites, with the commoners getting paid, kappa more or kappa times that of the elites. And you can do the same analysis, and you can find these solutions. And these two again are the elites and the commoners together are the carrying capacity for population, and these two are the associated values of nature and wealth that are sustainable by this system. Okay, and it's a little bit similar, so it's just a little bit different. Than you have a new parameter that appears here, this psi. And the psi is a ratio. It's a proportion of elite to commoner populations at equilibrium. Okay, and you can find on the scenario 3, you can find a delta triple star, which is the production rate that it maximizes the carrying capacity for population. Okay, and you can run pretty much the same scenarios as we've done before. This one is let's see, it has it's a scenario when you have a kappa of 100. So this is the elites get paid 100 times while the commoners get paid, and then what you get here, and then, if you look at what's happening here, nature gets depleted while the commoners and the elites are able to grow, and the elites can grow, but they take a lot longer because it takes for the commoners, because they're paid so little, it takes them a longer time to generate enough wealth for both of these guys to start growing. But eventually what happens is that as wealth gets produced and nature gets consumed, you sort of reach a plateau here for a little while between commoners and wealth and nature, but eventually nature bounces back because it doesn't get depleted fully, so it bounces back because of regeneration. In doing that, then this enables this essentially sort of shuts off the wealth, and eventually the populations of both the elites and the commoners are not able to keep up. Okay, so the regeneration of nature doesn't happen fast enough to stop this collapsing from happening. Okay. Look at another scenario here. This is probably a scenario that's closest to the one that it's run in the Benson model that I'll show you in the next video. But this has again a kappa of 100 and a delta of 10 to the minus 4. Okay, so this 10 to the minus 4 is about 15 times the delta in the first scenario, the sustainable delta. But essentially what you get here is it's an unsustainable scenario. And very simply, that's the one I showed you before in one of the previous slides. Nature gets consumed. In doing that, wealth gets produced, but eventually you run out of nature. Your wealth crashes because there's no more nature to be consumed, and the populations that were able to grow collapse eventually. And interestingly enough, like I said before, the elites are the last ones to go. This is another scenario that's another sub-scenario under scenario 3 that actually yields sustainable solutions. And what the authors did is that they tweaked some of the parameters, so the betas stayed the same, so the birth rate stayed the same, but for example, the commoners started not at 100 but at 10,000, and the elites started at 3,000. Okay, kappa was reduced to 10, so inequality was reduced, and then the production rate was kept close to, this delta is close to the optimum. So you need to keep an eye on this production rate. So this combination of conditions, more commoners, more elites, so bigger population, less inequality, and these birth rates were able to produce this sustainable scenario. This is the last scenario that's in the paper. This is a scenario that eventually leads to sustainability, but it's it leads to very small values of the stocks, and in this case the production rate was equal to that delta triple star that is the optimum. So what's embedded here is I'll summarize the results. Essentially, sustainability in this population nature model is tied to the reduction of inequality, to managing population growth, and managing nature depletion or consumption per capita. So this delta parameter is critical in these dynamics. This model allows the simulation of collapses that have been observed in history, like the Maya examples that we saw. But also, and perhaps more importantly, it highlights the combination of conditions that can yield sustainable population, nature, and wealth. Okay, so and that's probably the key in this case. Handy is this version of Handy is now being modified to introduce several improvements. First, a disaggregation of nature among renewable and non-renewable resources, so that you can actually discriminate. This nature regeneration rate, you can adjust it. Introduce government planning, setting limits on depletion of nature, inequality, and aspects like family planning, and also extending it to more than one region. So, for example, what happens if you have two handies, one for, say, the Americas, and one for Asia, and one for Europe, and you can allow for trade between these regions, trade of natural resources, trade of wealth, and trade of population, which is essentially migration. Then you start, having a much more powerful tool. So that's pretty much it. You will find a video of the Handy model in this YouTube link, so you can take a look at that. And hope you enjoy the video. You play with Handy, please play with Handy. Vary parameters, post insight and discussion on Facebook. I'm happy to see some discussions taking place. I want to see some more. So have a great week. Best of luck. Okay, thanks.